Statistics Unit Section 3. To get a sense of what the data looks like, we need to graph the data. And here we have an example of ages of students at Southwest Tech. And when we look at a large number of data values, it's hard to tell a trend, but graph it and we can see definitely where the bulk of the values are or any other information that might be helpful in knowing the characteristics of the data. In this example, the bulk of the students are at this younger range and fewer as it goes out to the right. When you have the majority of numbers on one end or the other of your graph, this is called skewed data. And oftentimes we will use a line to smooth out those rough edges. Here's another example. This is the top LPGA golfer in 2015, showing her scores that she had. And if we put a line to this data, this has a bell-shaped curve. Here's another example where we have a bell-shaped curve. We have IQ tests. The X's indicate the frequency. Most of the IQs, intelligence quotient, were in the 100, fewer in the 85, and so on down, and likewise the numbers get lower on the other side. The mean for this data is 100, and through calculation it was derived that the standard deviation is 15. When the data is graphed or distributed in this fashion, which results in this bell-shaped curve, the data is said to have a normal distribution. And there are many things that graph out or distribute themselves in normal distribution. IQ scores, as we just saw, heights of people, weights, measurements taken from production, manufacturing, service life of a product, car, batteries, tires, etc. It's often found that most naturally occurring events yield a normal distribution pattern. Here we have some examples from Consumer Reports showing us the price range of cars. The bulk of them are here in the middle, with fewer on this lower priced end of the graph and an equally fewer number priced at the higher end. We will see this bell-shaped curve in many areas, as we previously mentioned. Here's some examples showing wages of welders so that you can see where the bulk of them are here in this top graph at $14 with a fewer percent in the lower range, and symmetrically to the other side that same percentage fewer as well. Some characteristics about a normal distribution. It is symmetric, as I just said, in this bell-shaped, and what that means is that the right side of the curve is a mirror image of the left side. The mean will always be in the center of a normal distribution. Also, median and mode if it is a normally distributed data. The standard deviation is indicated by the shape of this normal distribution. It still will be bell-shaped, but if it has a small standard deviation, the span will be short, versus if we have a large standard deviation, it's more pancaked or flattened out over a larger range because the standard deviation is a bigger value. Let's look at an example of data that is normally distributed, and they're asking us to find the mean. No calculator is needed. It's just a matter of identifying that middle value. And there it is, 42. The raw values have already been calculated, and they use the mean and the standard deviation to graph this out. So it's a matter of us just looking at the graph. Mean is 42. Both of these graphs have the same mean value. As you look at them, they're both normally distributed, that classic bell shape, and in the middle is 20. The question is, which one has the larger standard deviation? If the standard deviation is larger, the range is going to be longer and wider, the variability is longer, and if you answered B, you would be correct. Some more characteristics of normal distribution. From the calculus world, we use calculus to determine the area underneath a curve, and it is set at 1, or translate that into a percentage. The area underneath the curve is all of the data, so that area of 1 is also equal to 100%. If we know the mean is in the middle, that means it's cutting the data in half. Half of 100% is 50%, so half of the data values will be to the left of the mean, and likewise half of the data values will be to the right of the mean. So you can make statements regarding your data knowing where the mean is and knowing that it's normally distributed with regards to 50% of the data. Furthermore, using that standard deviation, which is determining the shape of this, or I should say the span of this normal distribution, if you go out one standard deviation above and below the mean, and we're letting S stand for standard deviation here, that area will represent 68%, or 2/3 of the data will run between those two values on your graph. And here's an example. We have an engine with a mean horsepower of 275 and a standard deviation of 3. If we want to know where 68% of the engines are running from, their power levels, here on our normal distribution, we put the mean of 275 in the center of the graph. We're going to add 3 and subtract 3 from the mean, and that means 68% of the engines, since they are one standard deviation above and below the mean, range from 272 to 278 horsepower. If we go out 2 standard deviations above the mean and 2 standard deviations below the mean, this constitutes 95% of the data, almost all, but not quite, of the data. And here we go back to the engine with the mean of 275. We're going to add 3 plus 3, that's 2 standard deviations above the mean to get us to 281. Minus 3 minus 3, subtract 2 standard deviations from the mean. We have a range value of 269 to 281, and because it is 2 standard deviations above and 2 standard deviations below, this means 95% of any 3.5 liter V6 engine that you encounter should have peak horsepower between 269 and 281. The last characteristic that we'll look at for normally distributed data is going out 3 standard deviations. If we add 3 standard deviations, whatever that calculates out to be, to the mean, and subtract 3 standard deviations from the mean, this is equal to almost all, but not quite, 99.7% of the data values. And to show how this works, back to the engine again, we have our mean of 275. We're going to add 3 standard deviations. 3 times 3 is 9, or 3 plus 3 plus 3 brings us out to 284. Subtract 3 standard deviations from 275, which gives us a range of 266 to 284 power levels for 99.7%. Engines that have power greater than 284 or less than 266 are in that 0.3% that we haven't accounted for so far. Here, putting this into practice, another example, we have weld strengths that are normally distributed. They're asking us what the mean for this data is. Because it has been graphed already, it's just a matter of looking at the center or middle value, 39.6 for our mean, and they're asking us what the standard deviation is. No calculation needed other than maybe some help with the subtraction. Every one of these marks is a standard deviation away from the previous one, so any two adjacent numbers can be subtracted, and that will give us the standard deviation. So when you subtract, we end up with 2.2, and we could have done the same thing anywhere along here, getting the same standard deviation. You can now do some practice on these characteristics found on page 28.